Hello there, and welcome to the Sleepy Space Channel. Interstellar space is not a distance. It is a substance, and every property of it that sounds like a mercy turns into a hazard the moment it is measured precisely. Its emptiness is the finest vacuum ever encountered, and at 1/10 of the speed of light, that same emptiness becomes a continuous beam of 1 billion particles a second. Its cold is not the real difficulty, shedding heat is. Its radiation is made worse, past a certain thickness, by the shielding built to stop it. Its magnetic field is so weak it could not move a compass needle, and it organizes the entire galaxy. We have measured that field 3 times and obtained 3 answers. Tonight, we take each of those properties in turn, slowly, and look at it more closely than is comfortable. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is anything you need to carry. You are inside the shelter, and you have never once been anywhere else. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Part 1. The boundary. There is a place where the sun stops, and it is not where anyone would expect it to be. It is not the last planet. It is not the last of the small icy bodies, or the outer edge of the debris that circles beyond them. The sun's gravity reaches far past all of that, out into a shell of frozen material that may extend a substantial fraction of the way to the nearest star. Gravity is not what defines the edge. Something thinner does, and something stranger, and the place where it gives way is the beginning of everything this survey is about. The sun does not only shine, it leaks. A thin stream of charged particles pours away from its outer atmosphere in every direction at once, moving outward at roughly 400 kilometers per second, and it never stops. That stream is called the solar wind, and it is unimaginably tenuous. Near the Earth, it carries a handful of particles in each cubic centimetre, which is emptier than any vacuum a laboratory can hold. Yet because it is moving, it pushes. And because it pushes outward in every direction, it inflates a bubble. That bubble is the heliosphere, and its wall is not made of anything. It sits wherever the outward pressure of the solar wind happens to equal the pressure of the material outside it. There is no membrane. There is no shell. There is only an equilibrium between 2 thin things pressing against each other, and the position of that equilibrium is set by conditions on both sides. This is the first quiet correction the medium makes to our intuition. We think of interstellar space as beginning at a line, the way a country begins at a border. It does not. It begins wherever a balance is currently being struck, and balances move. The structure of that boundary has layers, and they were mapped in the only way they could be, which is by flying through them. Somewhere between 80 and 95 times the distance from the Earth to the Sun, the solar wind slows down abruptly. Up to that point, it has been moving faster than the speed at which pressure waves can travel through it, which means the wind has no advance warning of the obstacle ahead. At the termination shock, it is forced to become subsonic, and it heats and thickens and turns aside. Beyond that lies a broad, turbulent region where the wind piles up, moving sideways now, dragged into a long flow that trails away behind the sun. Only past that region does the wind finally lose. At a little over 120 times the Earth-Sun distance, the outward pressure of the sun's outflow falls below the pressure of what lies beyond, and the material outside takes over. That surface is the heliopause. It is the outer wall of the shelter, and it is the only physical boundary the sun maintains. 2 spacecraft have crossed it. They did not cross at the same distance, and the second one, crossing several years later, crossed closer in than the first. That single fact tells you more about the boundary than any model. The wall moves. It breathes in and out with the 11-year cycle of solar activity, expanding when the wind blows harder and contracting when it slackens. It is also lopsided, pushed in on one flank by the magnetic field of the material outside, so the distance to the edge depends on which direction you leave in. What the crossing actually looked like is worth describing precisely, because it is the only direct information humanity possesses about the medium beyond. Nothing was visible. There was no shimmer, no wall, no horizon, no change in the appearance of anything. The crossing was detected entirely by counting. 3 counts changed at once. The first was the number of particles arriving that had originated at the sun. That count fell away toward nothing, because the wind that had carried them had finally stopped. The second was the number of particles arriving from the wider galaxy, the fast nuclei that stream through the whole of interstellar space. That count rose by roughly 9% and stayed risen, because the screen that had been partially deflecting them was gone. And the third was the density of the plasma immediately around the spacecraft, which multiplied by something like a factor of 40. Inside the heliosphere, out at those distances, the plasma density is around 0.002 of an electron in each cubic centimetre. Outside, it measured somewhere between 5 and 8 hundredths. That jump is what confirmed the crossing. It is the single most important measurement humanity has ever made of the interstellar medium, and the manner in which it was made deserves attention because it is sobering. The instrument built to measure plasma density directly had failed decades before the crossing happened. It simply stopped working, far from the boundary, long before anyone knew whether the spacecraft would survive long enough to matter. So the density had to be inferred another way. When a shock front from a large solar outburst travels outward and eventually washes over the spacecraft, it disturbs the surrounding plasma and the plasma rings. It oscillates at a frequency that depends only on how many electrons are present. A different instrument, designed to listen for radio waves, can hear that ringing and convert its pitch into a density. The consequence is that the medium only tells us its density when something strikes it hard enough to make it sing. Between those events, which arrive years apart, the number is not measured at all. Everything we know about the density of the space beyond the sun comes from a handful of moments when a distant storm happened to reach a failing spacecraft and set the Emptiness humming. There were other surprises, and one of them remains unresolved. Models had predicted that the magnetic field would change direction sharply at the boundary, because the field carried outward by the solar wind and the field belonging to interstellar space have no reason to point the same way. When the crossing came, the direction barely changed at all. The strength rose, as expected. The orientation stayed close to what it had been. Nobody has fully explained that, and the two spacecraft that crossed measured somewhat different orientations from each other. The boundary itself is probably not smooth. The evidence suggests it is corrugated, rippled, and unstable in places, with interstellar material leaking inward and heliospheric material leaking outward through the wrinkles. Just outside it, there is a pile-up of neutral hydrogen, slowed and heated as it drifts against the obstacle, forming a broad wall of denser gas. That structure has been detected around other stars as well, and it is one of the very few ways an astronomer can observe another star's bubble at all. And the shape of the whole thing is genuinely unsettled. It may be a long, comet-like form with a tail streaming away for hundreds of times the Earth-Sun distance. It may be much shorter and blunter, closer to a croissant than a comet, with 2 lobes and no real tail. Both pictures are consistent with the data we have, which is a fair measure of how thin that data is. Two crossings. Both by spacecraft, whose instruments were designed more than half a century ago, powered by decaying radioactive material that gives up several watts of output each year. Their operators now switch off one instrument at a time to keep the others alive, and the commands take the better part of a day to arrive. A purpose-built successor has been studied, designed to travel 1,000 times the Earth-Sun distance and reach the boundary in about 15 years rather than 35, on less power than a household lamp. It has not been built. So this is the first thing to hold. The edge of the Sun's domain is not a place, but a balance. We have measured it twice. And everything that has ever lived, every organism in the history of this planet, every thought anyone has ever had, has taken place inside that bubble, on the sheltered side of a wall made of nothing but pressure. Beyond it, the counting begins. Part 2. The emptiness. The first thing anyone learns about interstellar space is that it is empty, and the figure usually given is about 1 atom in every cubic centimetre. In the neighbourhood the Sun currently occupies, the number is close to 1/3 of an atom per cubic centimetre. Roughly 2/10 of that is neutral hydrogen, and the rest is a mixture of free electrons, protons and helium. It is worth pausing on how thin that is, because the comparison is not intuitive, and it is genuinely remarkable. The air in an ordinary room contains about 25 billion molecules in each cubic centimetre. The local interstellar medium contains 1/3 of 1 atom in the same volume. The ratio between them is roughly 30 billion to 1. No number in everyday life prepares anyone for that. And it goes further. The finest vacuum that human beings have ever manufactured, in the most carefully constructed chambers, sealed and baked and pumped for weeks, still contains something on the order of 10,000 particles in each cubic centimetre. That means the best vacuum ever produced on Earth is about 100,000 times dirtier than the ordinary unremarkable space between stars. We have never made anything as empty as the space that fills almost the entire galaxy. This is the most reassuring number in astronomy. It sounds like safety. Nothing is there. Nothing can strike what is not there. Whatever else interstellar space might be, it is at least uncrowded. Hold on to that number, because it is about to be used against us. Emptiness is not a property of space alone. It is a property of space and of the observer's motion through it together. An object sitting still in the local medium is struck by essentially nothing. Over the course of a year, a stationary square centimetre encounters a few atoms. It is the most peaceful environment imaginable. Now attach a velocity. At 1/10 of the speed of light, a vehicle sweeps 3 billion centimetres of path in every second. Multiply that path length by 1/3 of an atom per cubic centimetre, and the result is about 1 billion atoms striking each square centimetre of the forward face, every second, continuously, for as long as the journey lasts. The medium has not changed. Nothing has been added to it. The emptiness has simply been converted into a flux by motion. And each of those atoms arrives carrying the energy that the vehicle gave it. At 1/10 of the speed of light, a hydrogen nucleus carries about 4.5 million electron volts. At 1/5 of light speed, it carries around 19 million. Those are not the energies of dust or weather. They are the energies of nuclear physics, the range in which particles knock atoms out of crystal lattices and break chemical bonds and leave permanent damage in solids. A leading surface crossing interstellar space at speed is, in every meaningful sense, the target of a particle accelerator that has been left running for 40 years. There is no way to make the medium thinner. There is no route that avoids it, because the medium is the route. This is what makes it different from every other hazard in spaceflight. Solar flares can be waited out. Orbital debris can be tracked and dodged. A planetary atmosphere can be entered at a shallower angle. The interstellar medium offers no such move, because the thing striking the ship is the thing the ship is traveling through, and the only variable that reduces the damage is speed, which is also the only variable that makes the journey possible at all. Shielding does not solve it either, in the way that word usually implies. A proton at those energies does not bounce. It buries itself a fraction of a millimeter into aluminium and stops there, depositing its energy inside the material. Over decades, that deposition adds up as displacement damage, atoms knocked out of position, tiny voids forming, the metal becoming harder and more brittle. A shield in that environment is not a barrier. It is a sacrifice, and it degrades on a schedule. There is a second property of the gas that shows how badly ordinary intuition fails out there, and it is one of the cleanest illustrations in all of physics. The local interstellar medium is hot. Its temperature is around 7,500 Kelvin, which is hotter than the visible surface of the Sun. And it would not warm you at all. Temperature and heat are not the same quantity, and interstellar space is where that distinction stops being an academic point. Temperature describes how fast the individual particles are moving. Heat describes how much energy can actually be transferred from one body to another. In a room, those two things track each other closely, because there are enough molecules that the fast ones deliver their energy constantly. In a medium containing a third of an atom per cubic centimetre, the particles are moving at the speeds you would find inside a flame, and there are so few of them that a surface immersed in that gas registers no measurable warming whatsoever. So the medium is simultaneously hotter than molten iron and completely incapable of warming anything. Both statements are true at the same time, and neither one is a trick of language. This is what a plasma at almost zero density does to the vocabulary we brought with us. That word matters as well. The interstellar medium is not a gas in the ordinary sense. It is partially ionized, which means a significant fraction of its atoms have lost electrons and carry charge. A charged medium responds to magnetic fields, conducts electricity, supports waves that a neutral gas cannot support, and cannot be treated as inert. It has structure. It has behavior. The emptiest environment in the galaxy is also a dynamic one, and it pushes back on anything that moves through it, weakly but continuously. By composition, it is almost entirely the two lightest elements. About 90% of its atoms are hydrogen, and about 9% are helium, and everything else in the periodic table together makes up roughly 1% by number. That last 1% is the material that stars have made and returned, and it is the reason planets and chemistry and observers exist at all. But by count, the medium is very nearly the same mixture the universe began with. Some of it reaches us. Neutral atoms carry no charge, so the heliopause does not deflect them. They drift straight through the boundary, past the outer planets, into the inner solar system, where sunlight and the solar wind eventually strip their electrons away. Once ionized, they are caught up in the outward flow and carried back out again. Those pickup ions are directly detectable near the Earth, which means interstellar material is arriving here continuously, in small quantities, and has been for the entire history of the planet. The wall is only a wall to charged particles. To neutral atoms, it is not there. The composition of what arrives carries information as well. The ratio of heavy hydrogen to ordinary hydrogen in the local medium is a surviving trace of the first few minutes of the universe, gradually diluted as generations of stars have processed the gas. Measurements along different nearby lines of sight give measurably different ratios, which means the local gas is not well mixed. It is a patchwork of material with different histories, sitting close together and not blending. There is one more coupling worth noting, because it explains the pile-up of gas just outside the sun's bubble. A fast ion and a slow neutral atom can exchange an electron on contact, without any real collision. The fast particle becomes neutral and keeps its speed, while the slow particle becomes charged and is caught by the magnetic field. This process, quiet and constant, is the main link between the charged and uncharged halves of the medium. It is what builds the wall of denser hydrogen outside the heliopause, and it is why the boundary is warmer and thicker than a simple pressure balance would suggest. The medium also pushes back measurably. Sweeping up particles means absorbing their momentum, and that produces a real drag on anything crossing at speed. The effect is negligible at ordinary velocities and rises steeply as a vehicle approaches the speed of light, which means the emptiness itself sets a practical ceiling on how fast anything can usefully travel. Speed does not merely become expensive at those velocities. It becomes self-limiting, resisted by the very thinness that was supposed to make the crossing easy. That is the picture then, and it is the opposite of the one the word emptiness suggests. The medium is the finest vacuum ever encountered, 30 billion times thinner than air, better than anything a laboratory can produce. It is also, to anything crossing it at speed, a continuous beam of nuclear energy particles that cannot be avoided, cannot be thinned, and cannot be fully stopped. It is hotter than the surface of a star, and it cannot warm a hand. It is made of charge, so it has structure, and it resists. The same number does both jobs. 1/3 of an atom per cubic centimetre. Whether it is the safest environment imaginable or a beamline depends entirely on how fast you are moving through it, and interstellar travel is defined by the requirement to move through it fast. Part 3. The dust. About 1 part in 100 of the interstellar medium, by mass, is not gas. It is solid. Interstellar dust is made of 2 broad families of material. One is silicate, essentially the same mineral family that makes up rock and sand, condensed out of the cooling outflows of dying stars. The other is carbonaceous, ranging from graphite-like flakes to loose amorphous carbon. In the colder and denser regions, both kinds acquire mantles of frozen material: water ice, carbon monoxide, ammonia, methanol, layered over the core like frost. The grains are small. The largest are around 1/4 of a micron across, which is 1/4 of a thousandth of a millimeter, comparable to the wavelength of visible light. The smallest are only a few nanometers, small enough that they behave more like large molecules than like solid objects, absorbing a single ultraviolet photon and then glowing in the infrared as they shed the energy. Between those limits, the population follows a steep distribution. For every grain of a given size, there are many more that are smaller, with the number in each size band falling off roughly as the size raised to the power of 3.5. That distribution is why the galaxy looks the way it does from inside it. Dust absorbs and scatters starlight. In the plane of the disk, where the dust concentrates, it dims what passes through by roughly 1 to 2 magnitudes for every 3,000 light-years traveled, which is to say it removes 1/2 to 3/4 of the light over that distance and keeps removing it. It also reddens what survives, because small particles scatter short wavelengths more efficiently than long ones. Blue light is stripped away preferentially, and the light that reaches an observer arrives redder than it left. This has a consequence that shaped astronomy for centuries. The dark lanes that run along the band of the Milky Way, The ones that look like rifts and gaps and holes in the sky are not gaps at all. They are dust in front of stars. For a long stretch of history, they were catalogued as regions containing nothing. They are in fact regions containing more than average, arranged in front of everything behind them. Most of the galaxy has never been seen in visible light from Earth, because most of the galaxy lies behind that screen. The grains also carry an alignment. They are not spherical, they are elongated, and they tend to line up with their long axes across the local magnetic field. Because of that alignment, starlight passing through a dust cloud comes out slightly polarized, with a preferred direction that encodes the orientation of the field it passed through. That is a remarkable piece of accidental instrumentation. The dust that hides the galaxy is also the only thing that lets us map the magnetic architecture of the material we cannot see into. Now attach the velocity again, because the same conversion happens here as with the gas, and it is more severe. Consider a grain 1/10 of a micron across, a completely typical one. Its mass is something like 2/1000ths of a billionth of a billionth of a kilogram. On any human scale, that is nothing whatsoever. Held in the palm, 1 trillion of them together would be invisible. At 1/5 of the speed of light, that grain carries about 3/1000ths of a joule of kinetic energy. That figure also sounds small. What matters is where it goes. The entire energy arrives inside a volume a few hundred nanometers across, in a few millionths of a billionth of a second. Solid material has no mechanism for absorbing energy that fast. It does not dent or deform or heat. It vaporizes explosively, and the resulting crater is very much larger than the grain that made it, because most of the damage is done by the material blowing outward rather than by the impactor going in. Integrated over a crossing, this stops being a question of individual collisions and becomes a budget. The relevant quantity is not how many grains are struck, but how much column of dust has been swept. At 1/5 of light speed, sweeping the column of dust contained in a few light years removes something on the order of 0.5 millimeter from the leading surface. 0.5 millimeter sounds trivial, and for a shielded probe with an ablative front layer, it more or less is. For a sail of foil a few atoms thick, which is what several of the more serious proposals actually depend on, 0.5 millimeter is the entire vehicle several thousand times over. And then there is the tail of the distribution, which is where the real problem lives. The size distribution is steep, so large grains are rare. But rare is not absent, and energy scales with mass. A grain 10 times the typical diameter has 1,000 times the mass, and therefore 1,000 times the energy. Push further out along the tail to a particle of 10 micrograms, still far too small for an unaided eye to see, still smaller than a speck of flour, and at 1/10 of the speed of light, that single particle arrives carrying several million joules. That is roughly the energy of a heavy truck at motorway speed, delivered into a point. The frequency of such an encounter over 4 light years is low. It is not zero. And there is no method by which such a particle could be detected in advance, because it is dark, cold, and moving with the medium, and any warning distance at those closing speeds would be measured in microseconds. Mitigation in every serious design is sacrificial rather than protective. The leading surface is understood to be consumed. It is made thick, made of something that ablates cleanly and accepted as a running loss. Some concepts propose flying edge-on to reduce frontal area, or projecting a shaped shield some distance ahead, so that impacts occur far from the vehicle and the resulting spray disperses before it arrives. That last detail matters more than it first appears, because a relativistic impact does not produce one event. It produces a forward-moving cloud of secondary debris traveling almost as fast as the vehicle, which then strikes whatever structure lies downstream. One grain becomes many. The grains do something else as well, and it is the reason the galaxy has stars at all. Two hydrogen atoms meeting in open space almost never combine, because the energy released has nowhere to go, and the pair simply flies apart. On the surface of a dust grain, the situation changes completely. Atoms land, wander across the surface, meet, and the grain carries away the excess energy. Essentially, all of the molecular hydrogen in the galaxy was assembled this way, one atom at a time, on surfaces a fraction of a micron across. Without the dust, there would be almost no molecular gas, and without molecular gas, there would be almost no star formation. The material that hides the galaxy is also the material that built it. There is an accounting problem hiding in that story which has not been resolved. Supernova shockwaves destroy dust grains efficiently, sputtering them back into the gas, and the rate at which they do so appears to be faster than the rate at which the winds of dying stars can produce replacements. By the simplest reckoning, the galaxy should contain considerably less dust than it does. Something is rebuilding grains inside the medium itself, probably by accretion onto surviving cores in the denser and colder regions, but the details are unsettled and the budget does not yet balance. The dust that reaches us is also filtered before it arrives. Small grains carry electric charge, and the sun's magnetic field, carried outward by the solar wind, deflects the smallest of them away from the inner solar system. The filtering strengthens and weakens over the 11-year cycle, which means the population of interstellar grains passing the Earth changes with the sun's mood. Larger grains are less affected and get through. So even the sample we collect here is biased toward the heavier end of a distribution we already know we are measuring in an unusually clean patch of the galaxy. There is a final wrinkle, and it is the kind of thing that makes local measurements untrustworthy. The sun currently sits inside a region that is unusually poor in dust. The cavity around us was cleared by supernovae, and its interior has far less solid material than a typical volume of the galactic disk. Every direct measurement humanity has made of interstellar dust, the grains captured by spacecraft in the inner solar system, the handful of candidate particles actually returned to Earth and examined under a microscope, samples this cleared-out neighborhood. The figures we work from are therefore an optimistic sample rather than a representative one. Says, elsewhere there is more. And the grains themselves are older than almost anything else in this survey. A silicate particle that condensed in the atmosphere of a dying star can drift through the medium for 100 million years without being touched. Nothing happens to it. It does not weather because there is no weather. It does not corrode because there is nothing to react with. It simply travels, cold and dark and unremarkable, until it meets something. And when it does, it supplies none of the energy. The grain is not moving quickly. It has been sitting almost still for geological ages. Every joule released in the encounter is supplied by the thing that ran into it. Part 4. The cold. There is a flaw to how cold anything in this universe can passively become, and it is not absolute zero. Everywhere, in every direction, space is filled with a faint microwave glow left over from the moment the early universe cooled enough to become transparent. That light has been stretching ever since, and it now corresponds to a temperature of 2.7 Kelvin, a little under 271 degrees below the freezing point of water. Any object left alone in the dark, radiating freely and receiving nothing but that glow, settles toward that value and stops. It cannot go lower without help. The universe has a resting temperature, and this is it. Interstellar space is not at that temperature. and it is not at any single temperature at all. It exists in phases, and their temperatures differ by 5 orders of magnitude. There are cold neutral clouds at 50 to 100 Kelvin, dense enough to hold themselves together, and cool enough that atoms move slowly. There is warm neutral and warm ionized gas at around 8,000 Kelvin, which together fill most of the volume of the galactic disk. There is hot ionized gas, blown out and heated by supernovae, reaching 1,000,000 Kelvin at densities of a few thousandths of a particle per cubic centimetre. And at the other extreme there are molecular clouds at 10 to 20 Kelvin, colder than the surface of any world in the solar system, colder than anything that occurs naturally on Earth. The Sun, at present, sits inside the hot phase. The cavity around us is a bubble of 1,000,000 Kelvin gas several hundred light-years across, carved open by a series of supernovae over the past 10 to 20 million years. Inside that cavity sits a small, warm cloud, and inside the cloud sits the heliosphere, and inside the heliosphere sits everything else. 3 nested regions, each defined by the pressure of the one outside it. So when someone says that interstellar space is cold, the statement is true only in a particular and misleading sense. What is cold is not the medium. What is cold is anything sitting in it that has nothing to warm it. And this is where intuition fails most completely, because the thermal problem of interstellar space runs in exactly the opposite direction from the one everyone expects. The difficulty is not staying warm. Warmth is easy. Any power source produces heat as a byproduct, and a vehicle carrying enough energy to cross interstellar space carries far more than enough energy to keep itself warm. The difficulty is getting rid of heat, and it is severe. On Earth, heat leaves an object by 3 routes. It conducts into whatever the object is touching. It convects away in the surrounding air or water. And it radiates as infrared light. In interstellar space, the first 2 routes do not exist. There is nothing to touch and nothing to circulate. Conduction and convection are simply unavailable. Only radiation remains, and radiation is remarkably inefficient at temperatures a human being could survive. The arithmetic is unforgiving. A radiating surface at 300 Kelvin, roughly room temperature, sheds about 460 watts for every square meter of area. That is the whole budget. A power plant producing 1 megawatt of waste heat therefore requires more than 2,000 square meters of radiator to stay in balance. 2,000 square meters is a structure larger than the vehicle it serves, an enormous, fragile array of thin panels and plumbing, unfurled in permanent darkness, facing directly into a medium filled with dust, traveling at 1/5 of the speed of light. Worse, the physics pulls in 2 directions at once. Radiated power rises with the 4th power of temperature, which means a radiator running at 600 Kelvin sheds 16 times as much heat per square meter as one running at 300. Every consideration of size and mass argues for running the radiators as hot as possible. Every consideration of habitability and materials argues for the opposite. There is no clean resolution to that contradiction, only a compromise, and every compromise costs area. Some designs try to escape the geometry entirely. One approach sprays hot liquid droplets into open space in a controlled sheet, lets them radiate as they fly, and catches them again at the far end, trading solid panels for a curtain of falling fluid. It is elegant on paper and has never been flown. Meanwhile, the cold itself is doing quiet damage, and this part is less dramatic than the thermal balance, but just as decisive over decades. Different materials contract by different amounts as they cool. A joint between 2 metals that was tight at room temperature works loose at 40 Kelvin, and a seal that held pressure on a workbench leaks in the dark. Polymers pass through a glass transition and stop being flexible. They become brittle, and a component that flexed 1,000 times a day begins to crack instead. Lubricants stiffen until moving parts stop moving. And hydrogen, which is the propellant of choice in almost every serious proposal because it offers the best performance per kilogram, boils away steadily, regardless of insulation, because there is no such thing as a perfect thermal barrier, and the journey lasts for decades. There is one genuine mercy in the environment, and it deserves acknowledgement because there are so few. Most spacecraft that fail do so because of thermal cycling, the repeated expansion and contraction of passing in and out of a planet's shadow 16 times a day for years. That cycling is what fatigues joints and cracks solder and eventually ends missions. In interstellar space, the cycling largely stops. There is no shadow to pass into and nothing nearby to heat one side. The environment is cold, but it is steady, and steadiness is worth a great deal. The floor itself has not always been where it is. The microwave background cools as the universe expands, which means it was warmer in the past and will be colder in the future. Early in cosmic history, the whole of space sat at room temperature, and later at the temperature of liquid nitrogen, and it has been sinking steadily ever since, toward a limit it will approach but never reach. The coldest the universe has ever been is now, and tomorrow it will be colder still, by an amount too small to measure and too certain to doubt. Against that flaw, the molecular clouds are a genuine curiosity. They sit at 10 to 20 Kelvin, while embedded in a galaxy flooded with starlight, which ought to warm them considerably more than it does. They stay cold because dust does two jobs at once. The outer layers of grains absorb the incoming visible and ultraviolet light and shield the interior from it, and then they re-radiate that energy in the far infrared, at wavelengths the cloud is transparent to, so the heat escapes rather than accumulating. The same material that makes those regions opaque is what allows them to shed energy efficiently. They are cold because they are dark, and dark because they are dusty, and dusty because dying stars filled them with soot. And a vehicle's thermal situation does not stay fixed because its power source does not. Radioactive material decays on a schedule that no engineering decision affects, and the thermocouples that convert its heat into electricity degrade on a schedule of their own. Available power falls year on year, while the radiator area stays exactly as large as it was built. A vehicle in its fifth decade is therefore over-equipped to shed heat it no longer produces, and under-equipped to do anything else. It is worth noting how deep this problem runs, because it is not confined to engineering. Instruments that need to see faint infrared light must be colder than the light they are looking for, which means cooling below the microwave background, below the universe's own floor. That can be done using layered sun shields to reach around 40 Kelvin passively, and then mechanical refrigerators and superfluid helium to reach fractions of a Kelvin. But every one of those refrigerators consumes power and produces waste heat, which must then be radiated away, which requires more area. Cold is not free. It is purchased with heat, and the heat has nowhere to go except outward, slowly, as light. And that outward glow has a consequence nobody designing such a vehicle can avoid. A structure with 2,000 square meters of warm radiator is, from the point of view of an infrared telescope, a bright and obvious object against a 2.7 Kelvin background. It is the single most detectable feature of any interstellar vehicle. Whatever else such a craft might conceal, it cannot conceal the heat it is throwing away, because throwing that heat away is the only reason it is still functioning. So the cold of interstellar space is not the hazard it appears to be. It is a flaw, set by the oldest light in existence, a set of phases spanning a factor of 100,000 in temperature, and a medium hot enough to melt iron that could not warm a hand. And the real difficulty it presents is not that a vehicle would freeze out there. It is that a vehicle would slowly cook itself in its own waste heat, and the only cure is to become larger, more fragile, and more visible. Part 5. The Dark. Interstellar space is dark, and darkness sounds like an absence. It is not. The space between stars is filled with light. The combined output of every star in the galaxy, scattered and reddened and spread across the whole volume, produces a radiation field with an energy density of roughly half an electron volt in each cubic centimetre. That is a real quantity of energy, present everywhere, in every direction, at all times. What makes it interesting is what it sits next to. The microwave background carries about 1/4 of an electron volt per cubic centimetre. The galactic magnetic field carries around 9/10. The population of fast cosmic ray particles carries approximately 1. 4 entirely unrelated phenomena, the light of stars, the afterglow of the beginning, magnetism, and relativistic particles, all carry energy densities within a factor of a few of one another throughout the galaxy. There is no established reason why they should. It is one of the quiet, unsolved questions in the study of the interstellar medium, and it is used as a working assumption in modeling galaxies, precisely because nobody can explain it away. Whatever couples these 4 things together, it holds them in rough balance across 100,000 light-years. What that light is not, however, is illumination. Brightness falls with the square of distance, and the numbers involved are severe in a way that is difficult to hold in the mind. Move 1 light-year from the Sun, and its brightness has fallen to about 1/4 billionth of its value at Earth. At that distance, the Sun would still be the brightest star in the sky by a comfortable margin, outshining Sirius. It would cast no shadow, warm nothing, and light nothing. It would simply be the brightest point. Move to the distance of the nearest star system, a little over 4 light-years, and the Sun becomes an ordinary bright star, comparable to a dozen others scattered across the sky, unremarkable and unnamed. Move to 56 light-years, and it disappears from unaided view entirely, into the background of stars too faint for the eye. That is the whole visible career of our star, from the only object that matters to nothing at all, across a distance that light crosses in less than 60 years. For anything crossing that dark, the practical difficulty is not seeing. It is knowing where you are. Every method humanity uses to navigate in space depends on reference points that behave predictably, and the interstellar sky provides remarkably few. Within the solar system, navigation works because planets are bright, close, and moving on known paths, and because radio signals from Earth arrive with timing precise enough to measure distance directly. Remove all of that, and the problem changes character. Parallax is the only direct positional cue available. As a vehicle moves, nearby stars shift against the more distant background, and the size of the shift gives the distance traveled. It works, but it works only against the handful of stars close enough to shift measurably, and the precision required is severe. Over a crossing of 4 light-years, the nearby stars move visibly, and the rest of the sky essentially does not. Radio contact degrades on the same inverse square law as light, and the numbers are humbling. A spacecraft at 160 times the Earth-Sun distance returns data at roughly 160 bits per second, slower than the earliest home modems, and only achievable because the receiving antennas on Earth are sensitive enough to detect signals weaker than the energy of a falling snowflake. Push the same transmitter out to 4 light-years, and the signal spreads across a volume so vast that a receiving dish would be catching a few particles of light per second. Data volume rather than data rate becomes the binding constraint. A probe that survives the crossing might be able to return a few hundred megabytes over the remainder of its operating life. The entire scientific yield of a 40-year voyage could fit on a memory card. And the delay removes control entirely. A round trip to the nearest star takes more than 8.5 years. Nothing can be steered, corrected, diagnosed, or rescued from home. Whatever the vehicle does, it does alone, using judgment built into it decades before the situation arose. There is one class of reference that does work, and it is the only reason autonomous interstellar navigation is considered possible at all. Some neutron stars rotate hundreds of times a second, sweeping beams of radiation past the rest of the universe with each turn. The regularity of those pulses rivals atomic clocks. Arrays of them are used as detectors for gravitational waves, precisely because their timing is so stable. A vehicle that can observe several of them simultaneously and compare the arrival times of their pulses against a stored model can calculate its own position in 3 dimensions without any contact with Earth. The technique has been demonstrated in orbit, using an instrument that fixed its own position to within a few kilometers using nothing but the ticking of dead stars. It is a strange kind of lighthouse system, beacons that nobody built, that will keep their time long after everything that uses them has stopped. The sky itself also deforms at speed. Move fast enough, and the apparent positions of all stars shift toward the direction of travel, an effect that grows with velocity and compresses the forward sky while thinning the one behind. At 1/10 of the speed of light, the shift is small but entirely measurable, and it must be corrected for in any positional fix. The navigational sky is not fixed even in appearance. And there is the ordinary, unglamorous problem that the target moves. Stars have their own motion through the galaxy, and the nearest ones drift measurably against the background within a single human lifetime. Aiming at where a star appears to be guarantees arriving where it used to be. A crossing must be aimed at a predicted future position, decades ahead, and the prediction must be good enough that a course correction late in the voyage can still fix the error with the fuel remaining. The color of that ambient light is not what most people would guess either. The interstellar radiation field is dominated in visible wavelengths not by the hot blue stars that draw the eye in photographs, but by the enormous population of cool red giants, which are individually unspectacular and collectively overwhelming. In the infrared, it is dominated by dust re-emitting energy it absorbed from starlight. So the average light of the galaxy, integrated over every source, is redder and cooler than the impression any photograph gives. The galaxy's true color is the color of old stars. It is also worth being precise about what a receiving antenna is actually doing at these distances, because the achievement is easy to understate. The signals arriving from the outer solar system are weaker by many orders of magnitude than the background noise of the receiving equipment itself, and they are recovered only because the signal is known in advance, its frequency, its structure, its expected timing, so it can be integrated out of the noise over long periods. Communication at interstellar distance is not a matter of shouting louder. It is a matter of knowing exactly what to listen for, and listening for a very long time. None of these techniques removes the fundamental condition, which is autonomy. A vehicle crossing that distance must diagnose its own faults, decide its own priorities, and choose what to record and what to discard, with no possibility of consultation. Every such decision must be anticipated by people who will very likely not be alive when it is made. That is a design problem of a kind spaceflight has never had to solve, and it is imposed entirely by the distance and the finite speed of light. There is one more thing about the dark that is easy to overlook, and it concerns the observers rather than the vehicle. Nobody on Earth has ever seen darkness. The night sky, as experienced from the ground, is roughly 100 times brighter than the true interstellar background, and that is on a perfectly clear night, far from any city, with no moon. The excess comes from air glow in the upper atmosphere, from sunlight scattered off dust in the plane of the solar system, and from starlight scattered by the atmosphere itself. Even in the darkest place on this planet, the sky is glowing. The genuine dark, the one with only the faint accumulated light of the galaxy in it, has been experienced by 2 spacecraft, both of them blind. The medium manufactures a good deal of that darkness for itself. Dust is opaque, and the plane of the galaxy is where the dust lives, so most of the stars in this galaxy have never been seen from Earth in visible light at all. We live inside a disk we cannot look through, and the darkness that makes interstellar space feel empty is partly the darkness of a screen with a great deal behind it. So the dark is not an absence. It is a radiation field in rough balance, with 3 other fields nobody has fully explained. It is a place where the sun is a star among stars within 4 light years. It is an environment in which position must be inferred from the timing of collapsed stars, because nothing else out there can be trusted to hold still. And it is, above all, quiet in a way no place on Earth has ever been, because there is nothing nearby bright enough to interrupt it. Part 6. The radiation. The galaxy is full of atomic nuclei traveling very close to the speed of light, and they are everywhere. They are called galactic cosmic rays, which is a name left over from an era when nobody knew what they were. They are not rays. They are the bare nuclei of atoms, stripped of every electron, accelerated over thousands of years by the expanding shock fronts of exploded stars, and then set loose to wander the galaxy indefinitely. They fill the interstellar medium at a flux of a few particles crossing each square centimetre every second, and they carry an energy density of about 1 electron volt per cubic centimetre, comparable, as noted, to the starlight and the magnetic field and the afterglow of the beginning. By count, they are mostly hydrogen. Roughly 87% are single protons, about 12% are helium nuclei, and everything heavier together makes up around 1%. That last 1% is the reason this hazard is unlike anything encountered on the surface of a planet. The energy a fast-charged particle deposits along its path scales with the square of its electric charge. A proton carries 1 unit of charge. An iron nucleus carries 26. Square that, and an iron nucleus deposits something like 676 times as much ionization per unit of path length as a proton of the same speed. It does not scatter and diffuse the way a light particle does. It drives essentially straight through matter, ionizing everything within a narrow cylinder around its track and throwing off a spray of knocked loose electrons that damage a wider halo around that core. The biological consequence has no terrestrial analog. Radiation exposure on Earth and the entire body of medical knowledge built around it is dominated by photons and light particles that deposit energy diffusely, so that damage is scattered randomly through tissue. A single heavy nucleus does something different. It damages a continuous column of cells simultaneously, every cell along a line, in a pattern that ordinary radiobiology has almost no experience of and cannot confidently extrapolate to. Inside the solar system, this is a manageable problem, largely because the sun does most of the work. The outflowing solar wind carries a tangled magnetic field with it, and that field deflects a large fraction of the lower energy cosmic ray population before it ever reaches the inner planets. The effect varies with the 11-year cycle, strengthening when the sun is active, and at its best it removes roughly 3/4 of the low-energy flux. Earth's own magnetic field and the mass of its atmosphere handle nearly all of what remains. Crossing the heliopause removes the first of those screens permanently. The measured cosmic ray count outside the boundary is around 9% higher, even at the higher energies that were never much affected, and at lower energies the increase is far larger. That 9% figure is one of the 3 counts that confirmed the crossing, and it is the clearest statement available of what the shelter has been doing. The numbers for human exposure are worth stating plainly. During the cruise to Mars, an instrument riding along measured a dose rate of about 1.8 millisieverts per day, roughly 2/3 of a sievert over a year. Career exposure limits for astronauts are set at around 600 millisieverts, which means a single year in ordinary deep space, still well inside the heliosphere, reaches a professional lifetime limit. Outside the boundary, the rate would be higher still. And then the remedy fails, in a way that is worth following carefully, because it is the most counterintuitive fact in this survey. Shielding a spacecraft works by forcing incoming particles to interact with nuclei in the shielding material. For low-energy radiation, this works well. The particle stops in the material, and the material absorbs it. For a high-energy iron nucleus, it does not work at all in that sense. The iron nucleus strikes an aluminium nucleus, and neither one stops. Both fragment. The iron becomes several lighter nuclei, still moving at nearly the original speed. The aluminium shatters as well, throwing off protons and neutrons and lighter fragments in the forward direction. The single incoming particle has become a shower of many, and the shower keeps traveling inward. The result is a curve with a minimum in it. Add aluminium shielding, and the dose falls at first because the low-energy component is being absorbed. Keep adding it, and at a certain thickness, the dose stops falling and begins to rise because the shield has become a productive source of secondary neutrons, which are electrically neutral, difficult to detect, and difficult to stop. Past that point, adding mass makes the situation worse. This is not a marginal effect. It is the central design constraint of deep space radiation protection, and it means the intuitive answer of building thicker walls is not merely expensive, but actively wrong. Hydrogen-rich materials do better, and for a straightforward reason. A hydrogen nucleus is a single proton with nothing to fragment into. It cannot shatter and produce secondaries because it has no parts. Water, polyethylene, and liquid hydrogen, therefore, stop more radiation per kilogram than metal does, and produce far less of the unwanted shower. This is why almost every serious long-duration design routes its water inventory around the crew compartment, so that the same mass serves twice, as drinking supply and as shielding. The alternative is to deflect rather than absorb, using a magnetic field generated by the vehicle itself. In principle, this works. Charged particles curve in magnetic fields, and a strong enough field would sweep them aside. In practice, the required field strengths mean large superconducting coils, which means substantial stored energy, structural loads from the magnetic forces themselves, and continuous refrigeration to keep the conductors superconducting. And refrigeration means waste heat, which returns us directly to the radiator problem, with its 2,000 square meters of panel. The problems in this environment are not independent. Each solution feeds a constraint back into another. The electronics suffer too, on their own timetable. A single heavy nucleus passing through a memory cell can flip a stored bit, and passing through a processor can corrupt a calculation in progress. Over years, accumulated impacts knock atoms permanently out of the silicon lattice, degrading performance in ways that cannot be repaired. This is why deep space computing hardware is typically several generations behind anything on a desk. Radiation-hardened parts are slow to design, slow to qualify, and conservative by necessity. A vehicle must also be able to rebuild its own software from redundant copies when a stored program is damaged, because there will be nobody to reload it. Two further facts complete the picture, and both are unresolved. The first is that cosmic rays arrive almost perfectly evenly from every direction. That is not because their sources are evenly distributed, they are not, but because the galactic magnetic field has been bending their paths for millions of years, scrambling their trajectories so thoroughly that all directional information is lost. Radioactive clock nuclei, produced by fragmentation along the way, allow that wandering time to be estimated at somewhere between 10 and 100 million years. A particle striking a spacecraft today was accelerated by a star that exploded before there were primates, and has been lost in the field ever since. The second is that the very highest energy cosmic rays carry, in a single atomic nucleus, roughly the kinetic energy of a well-struck tennis ball. Nothing in the known galaxy is confidently identified as their source. They are rare enough that they pose no practical hazard, and they remain one of the outstanding puzzles of high-energy astrophysics. There is a further complication in estimating the risk at all, and it is a matter of evidence rather than physics. Almost everything known about human radiation injury comes from acute exposures, brief, intense events, because those are the exposures that history has provided. Deep space delivers the opposite, a low, steady dose rate maintained for years, with a particle mixture that includes species essentially absent from any terrestrial exposure. Biological repair mechanisms behave differently under chronic low-rate damage than under a single large insult, sometimes better and sometimes worse, and there is no dataset that settles which. The published risk estimates, therefore, carry error bars wide enough to change the conclusion. That gap is being closed slowly and deliberately. A ground-based facility now exists that can reproduce the full mixed spectrum, switching between ion species in rapid sequence to imitate what a body would actually encounter over a long voyage, rather than exposing samples to one species at a time. It is the only way the mixed field problem can be studied experimentally, and the results are still accumulating. There is one more grim detail about the shield's secondaries. Neutrons carry no charge, which means they are not deflected by magnetic fields, and they do not ionize directly. They travel until they strike a nucleus, and in a heavily shielded compartment, they can dominate the total dose while remaining the hardest component to measure. This is a crew compartment designed to be safe by every visible criterion can be receiving most of its exposure from particles produced inside its own walls. The practical summary is short. There is a hazard out there that cannot be dodged, arrives from every direction at once, is worsened by the obvious defense past a certain thickness, and delivers a career dose in about a year. It has been passing through this planet's magnetic screen and its atmosphere for the entire history of life, in reduced form, and the reduction has been substantial. Outside that shelter, there is no reduction at all. Part 7. The Field. Before going further, it is worth pausing to set out what has been established, gently, in order. We began at a boundary that turned out not to be a place, only a balance between two thin pressures, crossed twice, by instruments built half a century ago. Then the emptiness, which is the finest vacuum ever encountered and becomes a continuous particle beam the moment anything moves through it quickly. Then the dust, 1% of the medium by mass, harmless at rest and explosive at speed, with a rare tail that carries the energy of a truck in a grain too small to see. Then the cold, which is not the difficulty it appears to be, because the real thermal problem is shedding heat rather than gaining it. And then the dark, which is not an absence but a radiation field, and which removes every method we have of knowing where we are. 5 properties. Each of them sounded like a mercy, and each of them turned into its opposite under measurement. That is the pattern, and it continues. Now the magnetic field, which is so weak that it should not matter at all. The interstellar magnetic field in this part of the galaxy has a strength of about 3 microgauss. To put that in ordinary terms, it is roughly 150,000 times weaker than the magnetic field at the surface of the Earth, and something like 30 million times weaker than a magnet holding a note to a refrigerator door. Measured on its own, it is as close to nothing as a physical quantity gets while still being detectable. Measured against the medium it occupies, it is dominant. The energy density of that field works out to around 9/10 of an electron volt per cubic centimetre, which places it, as we have seen, in the same range as the starlight, the cosmic rays, and the microwave background. In a medium containing 1/3 of an atom per cubic centimetre, magnetism is not a minor correction. It is one of the principal forces present, and in many situations, it is the strongest. This is why the interstellar medium cannot be treated as a gas. A gas is a collection of neutral particles that bounce off one another and otherwise mind their own business. The interstellar medium is partly ionized, which makes it a plasma, and a plasma threaded by a magnetic field behaves in ways a gas never does. Charged particles cannot cross field lines freely, they spiral around them. The field resists being compressed and springs back when released. It supports waves that carry energy across enormous distances. And it couples every part of the medium to every other part, so that the medium behaves less like a room full of air and more like a single connected material. The consequences run through everything else in this survey. The field is why cosmic rays are as abundant as they are. Without it, a fast nucleus accelerated by a supernova would travel in a straight line and leave the galaxy in a few tens of thousands of years. With it, the particle spirals and scatters and wanders, staying trapped in the disk for 10 to 100 million years, which allows the population to accumulate to the density we observe. The field is the container. The radiation problem exists in its present severity because of it. The field is also why starlight passing through dust becomes polarized. The grains are elongated, and they align themselves with their long axes across the local field direction, so the dust screen acts as a very large and very imperfect polarizing filter. Measure the polarization of light from stars in many directions, and the geometry of the galactic field can be reconstructed from the ground. It is one of the few methods available for mapping something entirely invisible. The field organizes the medium at every scale. It draws gas into filaments and sheets, it channels flows along preferred directions, and it provides a substantial fraction of the pressure that holds the disk of the galaxy up against its own weight. Where the gas is denser, the field is stronger. The strength scales roughly with density raised to a power somewhere between 1/3 and 1/2, so inside a molecular cloud, the field is 1,000 times stronger than the local value, measured in milligauss rather than microgauss. Inside those clouds, magnetic pressure is one of the main forces resisting collapse, and how a cloud eventually sheds enough of it to form stars is a problem that remains open. At the heliopause, the field does something that can actually be seen in the data. An interstellar field line approaching the sun's bubble cannot pass through it, because the plasma inside carries its own field, and the two cannot simply merge. So the external field drapes around the obstacle instead, bending and stretching and intensifying as it goes, the way grain in wood bends around a knot. That draping is why the field measured just outside the boundary is not the field of undisturbed interstellar space. It is a distorted local version of it, and the distortion depends on exactly where the crossing occurred. This produces one of the more honest embarrassments in the subject. There are three independent determinations of the local interstellar magnetic field. Two come from the spacecraft that crossed the boundary and measured it directly, at different places and different times. The third comes from mapping a narrow ribbon of energetic neutral atoms observed from Earth orbit, whose position appears to be controlled by the external field geometry. The three do not agree. The differences run to tens of % in strength and tens of degrees in direction, and the two direct measurements disagree with each other as well as with the remote one. Draping explains part of it. Something else may explain the rest. The honest summary is that humanity has measured the magnetic field of interstellar space 3 times and obtained 3 answers. There is one place where this field is unambiguously good news, and it concerns the hardest unsolved problem in interstellar flight. Leaving is difficult, but at least conceivable, because the energy can be supplied from home, by a laser, by a launcher, by something built at leisure in the solar system and left behind. Arriving is a different matter. A vehicle at 1/10 of light speed carries an enormous amount of kinetic energy, and shedding it conventionally requires as much propellant and as much energy as acquiring it did. Carrying the fuel to stop means accelerating that fuel first, which multiplies the departure cost enormously. A conducting medium, threaded by a magnetic field, offers a way out. A large loop of superconducting current, or a plasma structure sustained by one, generates a magnetic field of its own that interacts with the interstellar plasma streaming past. The interaction produces drag. It is not a strong effect, but it requires no propellant. It works continuously, and it grows stronger as the medium gets denser. A magnetic sail deployed at the far end of a voyage could in principle bleed off speed over years without carrying a gram of fuel. The complication is that the drag depends on the density of the medium, and the density along any real route varies by orders of magnitude on scales of a few light years. A braking system whose performance depends on conditions that will not be known until they are encountered is a difficult thing to plan an arrival around. There is another way of reading the field remotely, and it works across the whole galaxy rather than only nearby. Radio waves from distant sources arrive polarized, and when polarized radio waves travel through a magnetized plasma, the plane of their polarization rotates by an amount that depends on the field strength along the path and on how many electrons that path contained. Measure the rotation at several frequencies, and the field along that line of sight can be extracted. Thousands of such measurements have been assembled into maps of the galactic field, and they show a field with 2 components, an ordered part that follows the spiral arms, and a turbulent part of comparable strength that does not. The local direction of the interstellar field is therefore partly systematic and partly random, and which of the 2 dominates depends on the scale being asked about. The dust participates in this as well, more than it first appears. Grains in the medium acquire electric charge, from ultraviolet light knocking electrons off their surfaces, and from electrons sticking to them out of the surrounding plasma. A charged grain gyrates around field lines just as an ion does, only far more slowly because of its mass. This means the dust and the gas are dynamically coupled rather than independent populations, and the field partly determines where the solid material in the galaxy ends up. The same coupling is what filters the smallest grains out of the inner solar system. The field also steers what reaches us. The flow of the local cloud past the sun is guided by the field lines threading it, which means the direction from which interstellar material arrives and the rate at which it arrives are set by a magnetic geometry we have measured 3 times and disagreed about each time. There is a smaller consequence worth noting as well. Because the medium conducts, anything moving through it at speed induces currents in it, and those currents produce fields of their own that push back. A vehicle in interstellar space is never magnetically isolated. It is coupled to the material around it, weakly and continuously, and it drags a wake of disturbance behind it that will still be dissipating long after it has gone. And there is a last, quieter fact. In a magnetized medium, nothing charged travels in a straight line. Every proton, every electron, every charged dust grain follows a helical path around a field line, drifting slowly along it. The only things that move in straight lines out there are light and neutral atoms. Everything else in interstellar space is turning, permanently, around a field too weak to move a compass needle. Part 8. The clouds we pass through. There is an assumption buried in everything said so far, and it needs to be removed. The assumption is that the medium stands still and the solar system stands in it. Neither is true. The sun is moving through the local material at about 26 kilometers per second, and the material is moving as well, and the conditions around the solar system are therefore not a fixed environment, but a passing one. What the sun sits in today is not what it sat in 100,000 years ago, and not what it will sit in 100,000 years from now. At present, the solar system is inside a warm, partly ionized cloud, roughly 30 light-years across. Its density is close to 1/3 of an atom per cubic centimetre, the number this whole survey has been built on, and its temperature is around 7,500 Kelvin. It is unremarkable by galactic standards, a wisp, a thin patch of slightly denser gas inside a much emptier volume. The sun appears to have entered this cloud within roughly the last 10,000 years. In astronomical terms, that is not merely recent, it is essentially now. Every measurement of the interstellar medium ever made by human instruments has been made inside a cloud the solar system arrived in after the last ice age ended. And it appears we are already near its far side. The sun sits close to the boundary between this cloud and a neighboring one, a separate body of gas with its own velocity and temperature, which happens to contain the nearest star system. Whether the solar system is properly inside the first cloud, already inside the second, or somewhere in the interaction region where the two press against each other is genuinely unsettled. The measurements are consistent with more than one answer. Zoom out, and the setting changes character again. Both clouds sit inside something enormous and almost empty, a cavity of million Kelvin gas, several hundred light-years across, at a density of a few thousandths of a particle per cubic centimetre. That cavity was not always there. It was blown open over the past 10 to 20 million years by a series of supernovae, a cluster of massive stars that formed together, lived briefly, and exploded in succession, each blast pushing the material further out. Its walls are a shell of swept-up gas, compressed by everything that pushed against it. And that shell is where much of the nearby star formation is now happening. The famous nurseries within a few hundred light-years of the Sun are not scattered at random. They lie on the surface of that expanding shell, in a coherent structure, which is strong evidence that the explosions that carved the cavity also triggered the star formation around its edge. The neighborhood is not a static container. It is the inside of an explosion, still expanding, with new stars forming on its walls. Now the consequence, which is where this becomes a fact about the shelter rather than a fact about the scenery. The heliosphere's size is set by a pressure balance as established at the beginning. Solar wind pushing out, interstellar material pushing in. Change the external pressure and the boundary moves. The Sun's output is roughly constant on these timescales. The external conditions are not. The current cloud has a third of an atom per cubic centimetre. A cloud 100 times denser, 30 atoms per cubic centimetre, an entirely ordinary object, far from the densest thing in the galaxy, would compress the heliosphere substantially. A dense enough encounter could push the heliopause inward past the outer planets, and in the more extreme scenarios that have been examined, inside the orbit of the Earth. If that happened, the screening effect would go with it. The 3/4 of the low-energy cosmic ray flux that the heliosphere currently deflects would arrive instead. Interstellar dust and neutral gas would reach the inner solar system in quantities it does not now receive, loading the upper atmospheres of the planets with material from outside. None of this requires anything unusual to occur. It requires only that the solar system's ordinary motion carry it into an ordinary cloud. There is physical evidence that something along these lines has already happened. A radioactive isotope of iron, produced almost exclusively in supernovae, and with a half-life short enough that none should survive from the formation of the solar system, has been found in deep ocean crust and in samples returned from the Moon. It sits in layers corresponding to a few million years ago, and to an earlier episode before that. The straightforward interpretation is that the solar system passed through the expanding debris of nearby explosions and swept some of it up, and that a trace of that passage is now sitting in the sediment of this planet's sea floor. The local medium is also far more finely divided than the simple picture suggests. Careful absorption line work toward nearby stars reveals at least 15 distinct cloudlets within 50 light-years, each with its own velocity, its own temperature, and its own composition. They are not blended. They sit adjacent to one another, moving at different speeds, retaining different chemical histories. The medium in the immediate neighborhood is a patchwork rather than a bath, and transitions between patches may take only a few thousand years, a timescale shorter than recorded history. Which means the 4 light-years between here and the nearest star are not a fixed corridor. The material in that gap is flowing across the route at tens of kilometers per second, changing composition along the way, with a cloud boundary somewhere in the middle of it. A density measured now, along the line of sight, describes the material currently in transit and not the material a vehicle would meet in 50 years' time. It is worth being concrete about what a compression would actually feel like from inside, because the effects are not evenly distributed. The heliosphere does not merely shrink, it changes character. A far greater flux of neutral hydrogen would penetrate to the inner solar system, where sunlight would ionize it, and the solar wind would pick it up, loading the wind with mass and slowing it. Interplanetary space would become dustier. The upper atmospheres of the planets, which respond sensitively to the particle environment above them, would be working against conditions they have not seen in a very long time. None of this constitutes an event. It is a change of setting, arriving over thousands of years, and it has almost certainly happened before. How often is hard to establish, because 2 different records have to be aligned, and neither is complete. On the astronomical side, estimates of how frequently a star like the Sun encounters dense material suggest passages through molecular gas several times over the age of the solar system. On the geological side, the traces are subtle and easily overwritten. The radioactive iron in the sea floor is the clearest single line of evidence, and it points to a passage through supernova debris rather than through a cold cloud, which is a different kind of encounter with a different signature. The cavity around us is also not unique, and that matters for understanding how ordinary all of this is. A substantial fraction of the volume of the galactic disk is filled with similar bubbles, blown open by generations of massive stars, and they intersect and merge and share walls. The structure of the medium at large scales is less like a fog and more like a foam, thin, hot interiors separated by denser shells, with the cold material concentrated in the walls. The sun occupies one of the bubbles. It did not always, and it will not indefinitely. There is also an unresolved question about the shape of the shelter that bears on all of this. The heliosphere's overall geometry depends on the external field direction and on the ram pressure of the flow past it, and neither is known precisely. Some models produce a long, comet-like tail, extending hundreds of times the Earth-Sun distance behind us. Others produce a short, blunt, two-lobed form with essentially no tail at all. The two pictures imply very different environments in the trailing direction, and both remain consistent with the available data. Even the flow itself may not be steady. Measurements of the interstellar wind's inflow direction, made by different missions decades apart, differ slightly. The differences are small and the uncertainties are real, but taken at face value, they suggest the flow past the sun is changing on timescales of decades rather than millennia. So the picture that emerges is not of a static setting, but of a slow drift through weather. A star moving through a patchwork of thin clouds, inside a cavity blown open by explosions, on a shell where new stars are forming, carrying with it a bubble whose size is determined by whichever patch it currently occupies. The shelter is real. It is also provisional, and its dimensions are set by conditions the solar system does not control and did not choose. Part 9. The chemistry of the cold. Everything described so far has concerned the thin phase of the interstellar medium, the warm, nearly empty gas that fills most of the volume of the galaxy. That phase holds almost none of its mass. The mass is somewhere else. It is in the cold, dense clouds, which occupy a negligible fraction of the disk's volume and contain a large fraction of what the disk is made of. And those clouds are the most chemically active places in the galaxy, which is not what the word interstellar leads anyone to expect. A molecular cloud holds between 10,000 and 1,000,000 particles in each cubic centimetre. Compared with the local medium, that is an increase by a factor of tens of thousands to millions. Compared with the air in a room, it is still an extraordinarily good vacuum, better, still, than anything a laboratory can produce. Both comparisons are true at once, and holding them together is the only way to think clearly about these regions. The temperature is 10 to 20 Kelvin. That is colder than the surface of Pluto, colder than any natural place in the solar system except the permanently shadowed floors of a few polar craters. And these clouds are enormous. The largest span tens to hundreds of light years and contain millions of times the mass of the Sun. They are also chemically rich in a way that took a century of radio astronomy to establish. More than 200 distinct molecular species have now been identified in the interstellar medium. The list begins with the obvious: molecular hydrogen, carbon monoxide, water, ammonia, and then continues well past the point where anyone expected it to stop. Methanol, formaldehyde, acetic acid, simple sugars, long chains of carbon atoms with nitrogen on the end, molecules that on Earth are associated with kitchens, laboratories, and living things, present in quantity in the coldest and darkest volumes of the galaxy. Large carbon molecules are everywhere. Flat sheets of fused aromatic rings, the same structural family as soot, are so widespread that they carry a substantial fraction of the galaxy's carbon and dominate its infrared emission. Closed carbon cages of 60 and 70 atoms, the football-shaped molecules first assembled in a laboratory that was attempting to reproduce the conditions around a carbon-rich star, were subsequently confirmed to exist in interstellar space in exactly the environments the experiment had been imitating. The mechanism by which all of this assembles is worth describing, because it explains why the coldest places are the most productive. At 10 Kelvin, almost everything that strikes a dust grain sticks to it. Over hundreds of thousands of years, the grain builds up a mantle of ice. Water, carbon monoxide, methanol, ammonia, layered in the order they froze. Inside that ice, atoms and simple molecules can still creep slowly across the surface and across each other, and cosmic rays penetrating the cloud break bonds and create reactive fragments. Given 1,000,000 years, which the cloud has in abundance, complexity accumulates. When a nearby star eventually forms and warms the surroundings, the mantles evaporate and release everything that was built in them into the gas, where radio telescopes can finally see it. So the chemistry is slow, surface-based, and driven by radiation. It is the opposite of chemistry as practiced on Earth, which is fast and warm and happens in liquid. And it produces, over the lifetime of a cloud, the precursors of the molecules that biology later uses. Amino acids have been found in meteorites. Their precursors have been identified in interstellar clouds. The chemistry that precedes life begins in the medium, not on the planets. Almost none of this can be seen from outside. A dense cloud dims background starlight by tens of magnitudes, factors of thousands to billions, which makes its interior not merely dark but observationally sealed at visible wavelengths. Only radio and infrared light escapes, because those wavelengths are long enough to pass around the dust grains rather than being scattered by them. For most of the history of astronomy, these regions were recorded as holes, places where the stars stopped. The cold interiors persist, despite being embedded in a galaxy flooded with light, and the reason is the dust again. The outer layers absorb the incoming ultraviolet and visible light, shielding everything behind them, and then radiate that energy away in the far infrared, at wavelengths the cloud is transparent to. Energy comes in as visible light and leaves as heat radiation that passes straight out. The cloud is cold because it is opaque, and opaque because it is dusty. Cosmic rays are the exception to that ceiling. They penetrate where starlight cannot, and inside the deepest parts of a cloud, they are the primary source of ionization. Every ion they create begins a chain of reactions, because ions and neutral molecules react readily, even at 10 Kelvin where nothing else does. The radiation that makes the medium hazardous to cross is also the engine that drives its chemistry. There is a long-standing puzzle sitting in the middle of all this. Starlight passing through the medium shows roughly 500 absorption features that do not correspond to any identified substance. Some are broad, some narrow. They have been catalogued for more than a century and studied continuously, and they are known collectively as the diffuse interstellar bands. Only one family of carriers has ever been securely identified, and it turned out to be one of those large carbon cages in ionized form. The remaining several hundred features are produced by something present throughout the galaxy in appreciable quantity, and nobody knows what it is. There are also molecules out there that behave in ways no laboratory sample does, because the conditions cannot be reproduced. Some interstellar species, given a steady supply of energy from a nearby star, will amplify passing microwave radiation coherently, the same principle as a laser operating at radio wavelengths, across volumes larger than the solar system. These natural masers produce beams so compact and so bright that they can be used as reference points for measuring positions and motions across the galaxy with extraordinary precision. A cloud of water vapor, cold and thin and enormous, becomes an instrument. The chemistry also keeps records. The ratio of heavy to light isotopes in an interstellar molecule depends on the temperature at which it formed, because the heavier version binds slightly more tightly and is favored in cold conditions. Measure the isotope ratios in a cloud's molecules, and its thermal history can be reconstructed, where it was warm, where it was shielded, how long it has been sitting at 10 Kelvin. The same signatures survive in comets, which is how a comet can be identified as material that formed far from its star rather than near it. None of this chemistry proceeds quickly. Reaction rates at 10 Kelvin are so slow that most of the pathways familiar from a laboratory simply do not operate. What makes the complexity possible is not speed, but duration. A molecular cloud has tens of millions of years, and a dust grain in it has nothing else to do. Given enough time, a rate that seems negligible becomes an inventory. For anything crossing the medium, the dense phase is a change of category rather than a change of degree. The particle flux on a leading surface scales directly with the density of what is being swept. Go from 1/3 of an atom per cubic centimetre to 1,000,000, and every number in this survey rises by a factor of several million with it. The gas load, the dust load, the erosion rate, the induced drag, all of it multiplies together. Crossing a molecular cloud at 1/10 of the speed of light is not a hazard that shielding addresses. It is a different problem, and no proposal treats it as survivable. The saving grace is statistical and worth stating plainly, because it is one of the few genuinely favorable facts available. Molecular clouds fill almost none of the volume of the disk. The 4 light-years to the nearest star contain no such cloud, and the route ahead is thin, warm, and comparatively clear. That is a fact about this particular corridor at this particular moment in the Sun's orbit. It is not a fact about interstellar space, and it will not be true of every route, or of this one indefinitely. And these clouds do not last. They form out of colliding flows in the medium, hold together for tens of millions of years, give rise to stars, and are then dispersed by the radiation and winds of the very stars they produced. The cold phase of the galaxy is continuously recycled, assembled, used, destroyed, and assembled again somewhere else. The chemistry it builds is preserved only in the fragments that survive, in comets, which are samples of the pre-solar medium kept in cold storage, and in meteorites, which occasionally deliver the results to a laboratory bench. Part 10. What else is out there? The space between stars was given its name at a time when stars were the only things anyone could detect at those distances. The name has aged badly. It was a reasonable definition once. If the only objects visible across light years are luminous ones, then the volume between them contains, by definition, nothing worth naming. Every population discovered since has been a population that does not shine, and each discovery has been made only when instruments capable of finding that particular kind of darkness came into existence. The first were brown dwarfs. They occupy the gap between the largest planets and the smallest stars, massive enough to have collapsed under their own gravity and to glow from the heat of that collapse, but not massive enough to sustain hydrogen fusion in their cores. Having no fuel source, they simply cool, indefinitely, radiating in the infrared and fading as they go. They were predicted long before they were found, because there was no way to find them. They are common. In the local neighborhood, there is roughly 1 brown dwarf for every 5 or 6 stars, which makes them one of the most abundant classes of object in the galaxy. And their nearness is instructive. The third closest system to the Sun is a pair of them, at 6.5 light-years, closer than the great majority of stars visible on any night, and it was not identified until the 2010s. There is a solitary one at 7.5 light-years, with a surface temperature close to that of a comfortably warm room. It sits within the distance of the nearest dozen stars, and in visible light it does not exist. They also have weather. The nearest pair was the first substellar object to have a surface map made of it, and the map showed patchy cloud cover with condensates of iron and silicate, clouds of rock and metal, moving at hundreds of meters per second. An object closer to us than most of the named stars in the sky has storms, and we learned about them a decade ago. Then, the free-floating planets, which are stranger still. These are worlds with no star. Some were ejected from their birth systems by gravitational encounters during the chaotic early period when planets are still settling into their orbits. Others may have formed alone, collapsing directly out of a cloud without ever having a parent. Either way, they drift through the medium with no illumination, no heat source beyond their own residual warmth, and no orbital relationship to anything. They are detectable by one method only. If such an object passes almost exactly in front of a more distant star, its gravity bends and focuses that star's light, and the star appears to brighten and then fade over a period of hours to days. The event is a chance alignment. It never repeats, and the object is never seen, only its gravity is. To catch a handful of these events per year, surveys must monitor hundreds of millions of stars continuously. The statistics that come out of those surveys imply a very large population. Estimates vary considerably and carry substantial uncertainty, but the number of free-floating planetary mass objects in the galaxy is plausibly comparable to and may substantially exceed the number of stars. If that holds, then the majority of planets in this galaxy have no sun. And essentially none of them can be located in advance, because there is no method that finds them except waiting for one to pass in front of something bright. Then the visitors, which arrived recently enough to still feel like news. 3 objects on unbound trajectories have now been observed passing through the solar system, bodies that were not born here, fell in from interstellar space, rounded the sun on hyperbolic paths, and left again permanently. The first was identified less than a decade ago. All 3 were found on the way out, after closest approach, because none of them was bright enough to see coming. The first was peculiar, elongated, tumbling, showing a small acceleration that could not be accounted for by gravity alone, and displaying none of the visible outgassing that would normally explain such a push. No single explanation has been fully accepted. The second was unambiguously a comet, chemically similar to the comets of this solar system but with an unusually high proportion of carbon monoxide, which suggests it formed in a much colder region than the bodies here did. What matters more than any individual object is the inference. 3 detections in a handful of years, with survey capability that only recently became adequate, implies a background population of similar bodies throughout the local medium, a genuine density of debris passing continuously through the space we would have to cross. And then the remnants, which are the darkest population of all. Over the history of the galaxy, a great many massive stars have exhausted their fuel and collapsed. The result is on the order of 100 million stellar mass black holes, plus a comparable population of neutron stars, distributed throughout the disk. A neutron star can occasionally be detected if it is young and still hot, or if it happens to beam radio emission in a direction that intersects the Earth. The overwhelming majority satisfy neither condition. An isolated black hole with nothing falling into it emits nothing whatsoever. Exactly one isolated stellar mass black hole has been confidently identified. It was found by the same microlensing method, a distant star brightening slowly and then fading over several hundred days as an invisible mass drifted in front of it, a few thousand light-years away, with a mass of several suns. 1 out of an estimated 100 million. These remnants are also not distributed the way stars are. Both black holes and neutron stars receive velocity kicks when they form, thrown out of their birthplaces by asymmetries in the collapse, and they end up in a thicker, faster-moving component of the galaxy than the stars they came from. The dark population moves differently from the bright one. There is one more thing filling the gap, closer to home and easier to overlook. The Sun's own reservoir of comets extends outward for a very long way, possibly a substantial fraction of the distance to the nearest star. If the neighboring star maintains a similar reservoir, then the two may overlap or interleave or exchange members over long periods. The corridor between here and there is not a clean gap between two systems. It is a region where two sets of loosely held debris may already be in contact. The passing population also leaves traces here, which is one of the few ways its abundance can be checked independently. The Sun's outer comet reservoir is loosely bound, held at distances where the gravitational pull of the Sun is barely stronger than the pull of the galaxy as a whole. A passing star, or a passing dark body of sufficient mass, perturbs that reservoir on the way through, nudging distant comets onto new paths, some of which eventually fall inward. The long-period comets that arrive in the inner solar system therefore carry information about encounters that happened tens of thousands of years ago and hundreds of times further out. The medium's population is not purely a matter of statistics. It has measurable effects at this end. It is also worth appreciating how narrow the detection window is for a microlensing event. The alignment must be accurate to a tiny fraction of a degree. The background star must be bright enough to monitor. The observing program must happen to be looking at that patch of sky, and the brightening must be sampled frequently enough to distinguish it from the many other reasons a star's brightness varies. Miss any one of those and the object passes unrecorded. Every free-floating planet ever detected has satisfied all of them simultaneously, once, and will never do so again. Nor does the darkness of these objects mean they are cold in the ordinary sense. A young, free-floating planet retains the heat of its formation for a very long time and radiates it in the infrared. Some of the nearest substellar objects are warm enough that liquid water could exist in their upper atmospheres. What makes them invisible is not that they emit nothing. It is that they emit at wavelengths the eye cannot see, faintly, at distances where faint means undetectable. And the local census is still unfinished. The catalogue of systems within 20 light-years is estimated to be somewhere between 10 and 30% incomplete, and new members are still being added, almost all of them faint dwarfs or substellar objects found by infrared survey rather than by looking at the sky in the ordinary way. We are still discovering our own immediate neighbors, which leaves the summary for this part rather plain. There is no survey technique that can map dark bodies along a planned route in advance. They are found by chance or by their effect on light behind them, and both methods require the object to place itself in a very specific geometric relationship with an observer who happens to be watching. Anything crossing that space would be crossing a volume whose contents are known only statistically, and whose most abundant residents are, by construction, invisible. Part 11. The time it takes. Every hazard described in this survey is tolerable for an hour and unacceptable for a century. That single sentence is the whole of the interstellar problem. This is what separates the medium from every other environment humanity has entered. The deep ocean is hostile, and people go there and come back within a day. The surface of the moon is hostile, and the visits were measured in days, with the Earth close enough to see. Orbital stations are hostile, and they are continuously resupplied, repaired, and crewed in rotation. In every case, the required endurance is short, and behind it stands a supply line. Interstellar space removes both. The required endurance is measured in decades at the absolute minimum, and there is no supply line, because a supply line would have to make the same crossing. The speed arithmetic sets the scale, and it is unforgiving at both ends. The fastest objects ever sent out of the solar system are leaving at something like 17 kilometers per second, which sounds enormous, and is roughly 50 times the speed of sound in air, and would carry an object from one side of a country to the other in a few minutes. At that speed, the gap to the nearest star takes about 75,000 years. At a tenth of the speed of light, the same gap takes about 43 years, plus whatever time acceleration and deceleration consume. Between 75,000 years and 43 years, there is nothing that is both achievable with anything resembling existing technology and short enough to be called a mission. The gap in the middle is not a gap in ambition. It is a gap in physics. And relativity does not rescue this, which disappoints almost everyone who first encounters the idea. Time aboard a fast vehicle does run slower than time at home, and at high enough speeds, the effect becomes dramatic. At a tenth of the speed of light, it is not dramatic. The slowing amounts to about 1 part in 200, a few weeks gained over 4 decades of travel. It is a rounding error on the mission duration. Meaningful time dilation requires speeds above roughly 90% of light, and the energy required to reach those speeds is the obstacle that has never been surmounted, even on paper. Accelerating a modest vehicle to that velocity requires an amount of energy comparable to a substantial fraction of everything humanity produces in a year, and then the same again to stop at the other end. Relativity offers a genuine shortcut and prices it out of reach. Deceleration deserves its own consideration because it is the part most often skipped. Leaving is conceptually straightforward. The energy can be supplied from home by a laser array or a launcher or any large installation built at leisure in the solar system and left behind. Arriving cannot be done that way because there is nothing waiting at the far end to push back. A vehicle must either carry the means to stop, which means accelerating that mass at the start and multiplying the departure cost enormously, or find something at the destination to push against, the interstellar plasma itself, or the light of the target star. The medium that threatens the vehicle for the entire crossing is also the only thing available to stop it. The destination does not hold still either. Stars are not fixed points on a chart. They are objects in orbit around the galactic center, each with its own path, and the nearest ones drift measurably against the background within a single human lifetime. One nearby star moves by about the apparent width of the full moon every 2 centuries. A vehicle must therefore be aimed not at where a star appears to be, but at where it will be when the vehicle arrives, decades later, with the prediction good enough that a late course correction can still close the remaining error using whatever fuel is left. And the whole neighborhood is in motion. The sun, the target, and the cloud between them are all orbiting the center of the galaxy at roughly 230 kilometers per second, completing one circuit every 230 million years. The route is not drawn on a stationary map. It is drawn between 2 objects that are both being carried sideways at a speed vastly greater than the vehicle's own, and the geometry is preserved only because they are being carried together. Meanwhile, the vehicle decays on a schedule that no design decision alters. Radioactive power sources halve their output on a fixed timetable, and the thermocouples that convert their heat into electricity degrade independently, so available power falls faster than the isotope alone would predict. The spacecraft, now beyond the heliopause, lose several watts a year and are managed by switching off one instrument at a time, choosing which capability to surrender next in order to keep the others alive a little longer. That is not a malfunction. It is the designed, expected, orderly end of a mission that has already lasted longer than anyone promised. Cosmic rays degrade semiconductors continuously. Dust erosion removes surface material irreversibly, and there is no repair mechanism, so optical surfaces get worse monotonically for the whole voyage. Every seal, bearing, and lubricant has a service life that was measured on Earth over months and must be extrapolated across decades without maintenance and without replacement parts. Data storage media suffer their own radiation damage, which is why a vehicle must be able to reconstruct its own software from redundant copies when a stored program is corrupted. No machine humanity has ever built has operated continuously for 100 years. The longest lived are approaching 50. They are failing gradually and predictably, and they were built for a mission that was supposed to end at Saturn. For any crude concept, the problem multiplies. Closed-loop life support, air, water, and food recycled indefinitely, with no resupply, has never been demonstrated at the required reliability for more than a few years, and the failure modes tend to be biological rather than mechanical, which makes them harder to anticipate. Nobody who boarded such a vessel would arrive. The people who arrived would be strangers to the people who left, and every skill needed at the far end would have to be transmitted across generations inside a closed system with no outside reference. The energy accounting deserves one more look because it explains why the middle ground is empty. For ordinary speeds, the energy required scales with the square of the velocity, so halving the trip time costs 4 times as much energy. Approach a substantial fraction of light speed and the scaling worsens sharply because the vehicle's effective mass rises with its speed. The consequence is that there is no gentle progression from slow to fast. Modest gains in speed are cheap and useless. Useful gains are expensive beyond any current means. The curve has a shallow region that leads nowhere and a steep region that cannot be climbed. Light sail concepts sidestep part of this by refusing to carry the energy at all. The vehicle is a reflective surface, the energy source is an installation left at home, and the acceleration happens over a short window early in the voyage while the beam can still be aimed accurately. It is the only approach that makes the departure arithmetic tractable, because the mass being accelerated is small and the power plant never leaves. It also leaves the arrival problem entirely untouched, since there is no matching installation at the far end to catch anything. There is a smaller category of decay that gets less attention and may matter as much. Every judgment built into a vehicle's software was made by people reasoning about conditions they had never observed, using models of a medium measured twice. Those judgments do not degrade physically. They simply become older and less likely to match what is actually encountered with every year that passes. A vehicle in its 4th decade is operating on assumptions formed before it launched, in an environment nobody had visited. There is a final awkwardness, and it is more philosophical than technical. Technology improves. A vehicle launched now, crossing at whatever speed is currently achievable, might well be overtaken by a faster vehicle launched 50 years later, arriving first, having spent less time in transit. That observation has been used as an argument for waiting, and as an argument that waiting is a trap which never resolves, since the same reasoning applies equally at every future date. There is no obvious answer, and the disagreement is genuine. All of which converts every previous part of this survey into the same currency. The particle flux is a dose rate multiplied by decades. The dust erosion is a rate multiplied by decades. The thermal load, the power decline, the material fatigue, the isolation, none of them is severe in any single year. All of them are decisive across 40. Part 12. The Ordinary Universe. There is one more measurement to make, and it reframes every measurement that came before it. Take the local density of stars, roughly one system in every 250 cubic light-years. Then take the volume that stellar material actually occupies within that space, the volume of the stars themselves, the physical spheres of hot gas, and compare the two. Stars fill something like 1 part in 10 to the 23rd of the galaxy. That is a 1 followed by 23 zeros as the denominator. Planets and their atmospheres do not meaningfully change the figure. They are a rounding error on a number that is already almost entirely rounding. By volume, this galaxy is not a collection of stars with gaps between them. By volume, this galaxy is interstellar medium, essentially without exception, with a vanishing scatter of exceptions inside it. Which means everything surveyed here is not an extreme case. It is the baseline. The vacuum of 1/3 of an atom per cubic centimetre is not a hostile condition. It is the ordinary condition, and the one in this room is the anomaly. The temperature of 2.7 Kelvin is not an extreme. It is the resting state of the universe, and warmth is what requires explanation. The absence of any screen against fast nuclei is not a hazard particular to interstellar space. It is what the galaxy is like nearly everywhere, and the screening we live under is the special case. The darkness is normal. The silence is normal. The vast timescales, the slow surface chemistry, the field too weak to move a needle and strong enough to organize everything, all of it is simply how the universe is, almost everywhere, almost always. Which means the escalation in this survey has been pointing the wrong way the entire time. Each part appeared to describe something getting worse the further out we looked. It did not. What each part actually described was the removal of one more condition from a set so unusual that nothing living has ever experienced its absence. A magnetic field to bend the fast nuclei aside. A heat source at exactly the right distance, near enough to warm, far enough not to sterilize. An atmosphere dense enough to stop what the magnetic field misses. Liquid water, held in a temperature band a few tens of degrees wide. And, around all of it, a bubble of outflowing wind that removes roughly 3/4 of the low-energy cosmic radiation before it ever arrives. None of those things is common. Taken together, they are not merely rare, they are as close to unique as anything in this survey has been able to establish. The medium is not becoming more hostile with distance. It is becoming more ordinary. The shelter is what was strange. And that, in its way, is a settling rather than an alarm. Interstellar space is not waiting for anything. It has no capacity to threaten, because a threat requires attention, and there is nothing out there paying any. The word hostile implies a relationship, something set against something else, and no such relationship exists. The medium has held these conditions for something over 13 billion years. It will hold them long after the last star that currently shines has gone out, and long after the galaxies have drifted beyond one another's reach, in a universe that is mostly this, and was always going to be mostly this. The bubble is what is temporary. The sun has been inflating it for a little under 5 billion years, and will continue for perhaps 5 billion more, and then the wind will fail, and the boundary will collapse inward, and the medium will close over the place where the shelter was. It will not be an event. There will be nothing to mark it. The material that was inside will simply become part of what surrounds it, as most of the material in the galaxy already is. So it is worth stating plainly what has actually been established here, because it is not what the framing of the journey suggested. We measured a boundary and found a balance. We measured emptiness and found that it becomes a beam at speed, the same number, 1/3 of an atom per cubic centimetre, serving as the finest vacuum ever encountered and as an unshieldable flux of 1 billion particles a second, depending only on how fast you are moving through it. We measured dust and found erosion. We measured cold, and found that the difficulty is heat. We measured darkness and found a radiation field. We measured a negligible magnetic field and found the organizing force of the galaxy. We measured stillness and found weather. We measured sterility and found chemistry. We measured emptiness again and found a population that does not shine. And we measured all of it against time, which is where every one of those quantities becomes decisive. Every one of those conversions was already true before anyone looked. Nothing changed out there. What changed was the resolution of the looking. It is worth being honest about the foundations under all of it as well. Every figure in this survey traces back, directly or indirectly, to a very small body of direct evidence. Two spacecraft that crossed the boundary, several years apart, at different distances, carrying instruments designed more than half a century ago, one of which had already lost the sensor that would have measured the most important quantity. Everything else is inference, from absorption lines in the light of nearby stars, from the polarization of starlight passing through dust, from the rotation of radio waves crossing a magnetized plasma, from the brief brightening of background stars as invisible masses drift in front of them. These are extraordinarily clever methods, and they agree with one another to a degree that inspires reasonable confidence. They are not the same as having been there, which is why the three disagreeing measurements of the local magnetic field are the most representative fact in this entire survey. Not because the disagreement is scandalous, but because it is honest. We have looked at the space around our own star, from inside it and from just outside it, using the best available instruments, and obtained answers that do not quite match. The medium that fills essentially the whole of the galaxy remains, at the level of detail, a thing we are still learning to measure. And the shelter itself is doing more than it is ever credited with. 3/4 of the low-energy fast nuclei arriving from the galaxy are turned aside before they reach the inner solar system, and they have been turned aside continuously for the entire history of life on this planet. Not by anything designed, and not by anything that could have been arranged. By a wind blowing outward from a star at 400 kilometers per second for 4.5 billion years without pause. And so we arrive back where we started, which is the only place any of this was ever observed from. Everything that has ever lived has lived inside a bubble held open by a wind, drifting through a small warm cloud, inside a cavity blown open by stars that died before there were forests. Every thought anyone has ever had, every measurement in this survey, every instrument that made them, has existed on the sheltered side of a wall made of nothing but pressure. A wall we have crossed twice, with equipment designed half a century ago, and which we understand mainly by what stopped arriving on the far side. The space beyond it is not against us. It is not for us either. It is simply what the universe is, in almost every direction, for almost all of time, and it has been perfectly indifferent to the whole of that time passing. Let your breathing slow. Let the walls of the room settle back around you. There is a great deal of quiet out there, and none of it is looking this way. Sleep well, and good night.